Namaskar and welcome to this lecture on concrete engineering and technology. The subject of concrete engineering is acquiring tremendous significance as we continue to use more and more concrete in diverse conditions. We use new materials, new technologies. We have more experience from previously built structures. And we realize that concrete is not a maintenance-free material. Also, in recent times, there is a rising concern about quality and durability of concrete construction. So, in other words, a concrete engineer needs to update the understanding of concrete as a material and its properties. He should be aware of the development of special concretes and their properties, the applications, the limitations, be conscious of the limitations of the existing test methods and specifications, and work towards establishing new methods and specifications as may be required for new concretes. We also need to understand the issues in shifting to a more performance-based thinking rather than simply a prescriptive thought process. We must integrate words such as maintenance and repair in the overall life cycle of concrete. Concrete structures are not only designed, but they need to be maintained and repaired over their service life. And that is what needs to be integrated as an overall life cycle of concrete structures. And therefore, this course aims at revising the basic principles underlying concrete science and engineering, because without that, we cannot approach the subject of modern concrete or new developments in concrete. We need to develop a framework which helps us understand the present day scenario in concrete engineering as far as testing, specifications, use of new materials, applications, limitations. We should go through some issues in special and high performance concretes and their quality control and test, including performance-based thinking, durability, maintenance. So this is basically the outline that we will try to go through in this course. Let's review our understanding of reinforced concrete. Reinforced concrete basically consists of a reinforcing steel bar as shown here, and that bar is embedded in concrete. Now, concrete itself consists of, as is shown in this picture here, coarse aggregates which are shown as dark brown, embedded in paste. Now, paste is used loosely here because actually it is mortar if this aggregate is coarse aggregate, and if it is fine aggregate which is sand, then this diagram refers to mortar, and then indeed sand particles are embedded in cement paste. If we look at the neighborhood of a small particle, we have the aggregate particle here as shown, and this is surrounded by paste. However, in this small zone here, there is the so-called transition zone, and this transition zone, as we shall see later on, plays a very important role in determining the properties of the concrete. Now, if we look at a small element of paste, which is the cement and water hydrates, we find, or we could model this small element as comprising of solid CSH or hydration products, in which there are a lot of these pores. So this pore structure, now we will try to understand what is the genesis of these pores. We will try to understand what's the importance of these pores and how we try to control the amount of pores and so on, how do we measure the pores, and then try to understand how the concrete behaves as a material. Continuing from here, let's look at this particular picture here, which is a solid slice of concrete, real life concrete. We can see that these are large aggregate particles all over the place. which are suspended in a phase of mortar, which are these smaller particles somewhere here, all these smaller particles here, and then there is cement paste. This picture is modeled as shown here, that we have these larger particles which could be considered as coarse aggregate, we have these smaller particles which could be considered as sand, then we have these still smaller particles which are cement, and there is a lot of water or some amount of water which has been added to this whole mix. And if we model this mix in a volumetric manner, that all these coarse particles here or all these coarse aggregate particles are lumped into one place here, and that is what I have called gravel or coarse aggregate. Then all these smaller particles come in here as sand, cement particles find their place here, water finds its place here. We will find that some amount of air or void space is always an integral part of concrete. What this picture shows is that as far as concrete is concerned, no matter whether it's a normal concrete or a special concrete, one concrete or another concrete, for a given volume of concrete, we have a certain volume of coarse aggregate, a certain volume of sand, cement and water, and there is some air. The importance of this air component we will discuss later on, and we will also discuss how the constituents such as cement, sand and coarse aggregate changes in special concretes, and this change that we make in the concrete materials makes the concrete behave in a different manner. In other words, what we are saying is that normally we can consider concrete to be made up of coarse aggregates, fine aggregates, cement, which is OPC for all practical purposes to begin with, and water. However, increasingly mineral and chemical admixtures are being used in concrete as part of the materials to obtain or engineer the properties of fresh and hardened concretes. Concrete, as we shall see in this series of lectures, has different properties that we need to ensure that it has. Properties in the fresh state and properties in the hardened state. And the given mix that we have should satisfy the properties not only in the fresh state but also the hardened state. To reiterate what concrete engineers always talk about, paste is cement and water. Mortar is sand added to this paste. That is, mortar consists of cement, water and sand. Concrete, our normal understanding says, is coarse aggregate added to mortar. That is, concrete basically consists of cement, water, sand and coarse aggregate. This is largely understood. However, what is the need to change or reiterate this at this point in time? The idea basically is that once we understand this, then when we add special materials or new materials to this old combination of cement, water, sand and coarse aggregate, then we have to understand or we have to decide whether it will be counted towards the paste volume or the mortar volume or the coarse aggregate volume and so on. So keep this in mind as we go along in these lectures. Once again, this picture only reiterates what we talked about earlier. Concrete is a model of suspension of coarse aggregate particles in mortar. Mortar, on the other hand, is a suspension of fine aggregate particles in paste, and paste is a suspension of cement particles in water. So in other words, the only fluid component in the only fluid component in concrete is water. We add cement to it, make paste, then we add sand to that, we get mortar, and we add coarse aggregate to that, and then we get concrete. So this is basically the model that we will follow as we go along in this course. The suspension, as included here, deviates from a normal understanding of the word in the following ways. concentration of particles is very large, making it almost a paste. Now, differentiate between the word suspension and a paste. A paste, in the normal usage of the word, is a thick viscous material which may have a large concentration of solids. In the case of cement paste, the particles suspended in water also react with it. So that is to say that the paste is made up of reactive particles, and because of this reaction, the composition and properties of the paste need to be understood to be time dependent. As time progresses, more cement reacts with water, less cement is available for further reaction with water, and the formation of hydration products alters the properties of paste. It's not a paste in the sense that we have water and we have certain particles suspended in it, and the properties of that composition or that composite do not change with time. In this case, we have those particles reacting with water all the time, or at least till such time as the hydration reaction is complete, and this reaction leads to consumption of those particles and formation of new hydration products, and that alters the properties of the paste. So once we understand this, it helps us greatly in understanding the properties of concrete in all senses. In other words, paste is the only reactive phase. All other aggregates, which is whether sand or coarse aggregates, are simply inert fillers, which means that cement particles react with water, as we have said. The properties of cement paste changes over time as a result of this continued hydration, and hydration starts as soon as water and cement come in contact. Now, let us look at the basic processes in concrete engineering. From the point of view of a project, we normally have a specific condition or a set of specifications and a structural design and construction methodology, and then try to go through these steps. Now, what are the steps? We need to choose the constituents, what kind of cement, what kind of coarse aggregate, what chemical admixtures or whatever if they are being used, proportioning, which means how much of each of these constituents will be used, mixing those constituents, how will they be mixed, transporting these constituents from the site of mixing to the site of placement, placing. Now, placing refers to the concrete being placed at the actual site of placement. If a building is being constructed, the building site is the site of placement. However, the concrete is placed in a particular beam or a slab or a column, which may be at a height. If it's a foundation, it may be at a depth, and so on. So this placing here refers to the process by which the concrete actually brought to the site of placement, which is the building construction site, is actually placed in the final place or the final location where the concrete needs to be set. After the concrete has been set, it needs to be vibrated or consolidated. What process will be used there? And finally, the concrete needs to be cured. That is, we need to make sure that enough water is available to the cement to ensure complete hydration, or as complete a hydration as is possible. So in a project, after the specific conditions and specifications, the design and construction methodology, an engineer tries to understand or tries to look at how all these processes will be managed. Thus the discussion often is project specific, and the engineer needs to pick up the best option from those available. So for a particular project, one may choose a particular method of transportation. For a particular project, one may choose a specific constituent, a specific method of vibration. Sometimes vibration is not possible, and therefore you need to change the constituent materials, and so on and so forth. So a concrete engineer really needs to know the importance of all these processes and how they are interconnected, and that's precisely the objective of this course. We've often used the word special concrete. Now, what is special concrete? Given the fact that there are several processes involved, there is a certain range of the variables over which the operation or the process can be called normal. Now, if any of these processes goes out of that range or another special process becomes involved, the concrete needs to be treated as special. In other words, what makes a concrete or a concreting operation special? It could be the choice of materials. Other than the usual ordinary Portland cement, fine and coarse aggregate and water, we could use fibers, we could use chemical admixtures or mineral admixtures, and that makes the concrete special. Or mixing can be done in different ways. It could be mixed manually, which is done for very small projects or very small applications. We could use a small mixer that we often do in the laboratory studies, and then there is a ready mix concrete plant. So the mixing that is done in any of these places or in these places is quite different, and that makes the concrete, for the same ingredients and for the same proportion, the properties will be different because the mixing process is different. Transportation. Concrete can be transported in different ways. Conveyor belts, agitator trucks. Placing issues. Concrete is placed with shotcrete or tremie. Vibration. Concrete could be form vibrated, it could be needle vibrated. The environment of placing, where the concrete is actually placed. For example, in a factory, and that's where we make precast concrete elements, beams, girders, and so on. If it's underwater, it could be extreme hot or cold weather, or if the structure happens to be highly congested. Then the kind of concrete that is required in any of these environments is quite different. The property that we require for concrete, we may require high strength or low strength, we may sometimes require early strength, which is especially the case, for example, in a repair project. We may require a low heat of hydration, which is the case in case of a mass concrete project, and so on. Sometimes we use high flowing concrete when the reinforcement is very congested, as we shall see in this course. Curing conditions, gunny bags, plastic sheets, curing compounds, and so on. So the point is that once any of these conditions or any of these processes goes out of a normal range, we would call the concrete and the concreting operation as special. Now let's look at some of the examples of this slide. Let's look at materials. Now this is the moment we add these fibers to concrete, the properties change. But so also we need to change the properties of the mortar, the properties of the materials that we have otherwise selected for a normal concrete. Let's look at mixing. This is the process of manual mixing. So you can see that water is being dumped into this large pile here where all the ingredients have been put together, and the kind of mixing processes that will be completed in this, it will be different if the same proportion and the same material was mixed, for example, in a small laboratory mixer, or for example in an RMC plant mixer, that is a ready mixed concrete plant where concrete is mixed for commercial applications. So that's about mixing. Now let's look at transportation, how concrete is transported. This slide here shows transportation of concrete using a conveyor belt. This picture here on the left shows concrete being transported with an agitator truck. This drum here has to be kept rotating in order to ensure that the concrete does not set and stick to the sides of the drum. Depending on the time of travel, some chemical admixtures or something needs to be added to ensure that the setting process does not get started to an unacceptable level, because hydration anyway starts as soon as water and cement are in contact. It's only a matter of delaying that process. If we are transporting concrete in a conveyor belt, then concrete is being exposed to the atmosphere. That is, it is liable or it is likely to get dried in the process of being transported. And these are the things which we need to incorporate in our thought process when we are choosing the proportions, when we are choosing the materials, and so on. Let's look at placing. This process here, both of them, they refer to shotcreting. Shotcreting, as you can see here, is a process where the concrete is being deposited on the surface without any formwork on the other side. This makes this concrete very special. We cannot use the kind of concrete here for normal construction. On the other side, if we want to concrete using shotcrete as the process, we cannot use normal materials and processes. This slide shows construction of concrete with a tremie. Now, in this case, concrete is being deposited at depth, possibly underwater, using a tremie. Now, the concrete is being dropped all the length of this pipe, and it is ensured, or it needs to be ensured, that the pipe is always embedded in this concrete. As more and more concrete is dumped in, the concrete rises in this formwork here, and the construction process is completed. This slide shows concrete construction using a tremie. Concrete is allowed to fall through the pipe, and it needs to be ensured that the pipe is always buried in the concrete that has been placed. As more and more concrete is placed into the formwork, it rises up and gradually fills the total space, completing the construction process. Let's look at vibrations. We have form vibrators, we have needle vibrators, and sometimes we use roller compacted concretes, and we have form vibrators which are stuck or which are applied on the formwork, and the concrete within is vibrated. We have internal vibrators, which is the normal concrete practice, where the needle is inserted inside the concrete that has been placed, and the concrete is consolidated to remove the air, and so on. The environment of placing. This is a factory environment of concrete placement, where we get precast concrete elements. So the environment here is largely controlled. That is, it's not exposed to rain, it's not exposed to direct sunshine, and so on. Whereas this is a completely different environment. Concrete is being placed underwater, and we can see that divers are involved in the whole process. These are the reinforcing bars that you can see as concrete is being placed. This is an example of congested reinforcement in concrete construction. Now you can imagine that if concrete has to be placed around this structure or around this part of a structure, how difficult it is for concrete to flow through all these gaps, and as the concrete flows through these gaps, how it will be vibrated. So it requires a special concrete to be used so that concrete can find its way through the gaps of these reinforcing bars, which are very close to each other, and still be compacted. An example of special properties of concrete. These two pictures here show high workability concrete, and this method that we use to evaluate the workability of such concretes cannot be the normal methods such as the slump or the compaction factor. There are these tests like the slump flow or the U-tube test, which is used. We will discuss this in greater detail, but you can see that the slump flow here is nothing but how much is the spread of the concrete once the slump cone is removed, and this is a U-box test where the concrete is filled on one side of the U, and the barrier in the bottom is removed, and the concrete flows to the other side. If the concrete was to behave as a perfect or a fluid, then at the end of this process of concrete moving from one side to the other, the two sides will be exactly at the same height. In normal concretes, we do not even expect the concrete to be able to flow through the barrier here. As far as curing is concerned, these pictures here show three examples where curing is being done with the gunny bags or plastic sheets or application of water and curing compounds from outside, and so on. So what the moral of the story is that each of these processes has a normal range, and once we deviate from that range, this construction process becomes special, and therefore we need to have special concretes we need to use special materials and be aware of that in our thinking as far as quality control and specifications, test methods are concerned. Indeed, for a special concrete, the entire operation, all the processes have to be looked at more carefully. The choice and proportion of materials, method of transportation, placing and curing, all have to be specially designed, and special measures need to be taken for quality control and assurance in construction. Now, what are the properties of fresh and hardened concrete? As far as the properties of fresh concrete is concerned, workability, air content, segregation resistance, temperature and setting time. These are some of the fundamental properties that we will talk about in this course. As far as hardened concrete is concerned, characteristic compressive strength is something we are aware of. Tensile and or flexural strength is a requirement in certain special cases. Modulus of elasticity, the stress strain curve, creep, shrinkage, permeability, durability, all these are different properties of hardened concrete, and they need special methods or specific tests to be carried out in order to make sure that the concrete meets the requirements. Coming to the contents of this series of lectures, what we will try to do is revise the fundamentals of concrete. We will try to proportion concrete mixes. We will go through the stages of concrete construction. We will talk about special concretes. We will discuss a little bit about mechanisms of deterioration in concrete. We will talk about reinforcement in concrete structures. We will talk a little bit about maintenance of concrete structures. In other words, we will try to go through the subjects which a concrete engineer of the present day is often required or expected to know. This set of discussion here, the discussion here will help one who wants to study more about any of these issues in greater detail at any point in time. Please note that the discussion in this set of lectures will assume that this is not the first time that you are hearing about concrete, and perhaps this is not the last time you are hearing of concrete. I hope that in this set of lectures we are able to instill in you a sense of curiosity and better understanding as far as behavior of concrete is concerned. Now, revision of fundamentals of concrete, what we will try to do is overview of the course, which is what we are doing today. We will talk in detail or in some detail about constituents of concrete, properties of fresh and hardened concrete, hydration of cement and strength development in concrete. We will talk about quality control and the quality assurance issues in concrete construction. Coming to proportioning of concrete mixes, we will go back to this picture and we will talk of basic proportion, where only water, cement, sand and coarse aggregate is involved, and we will talk about additional topics or special topics in proportioning when chemical admixtures or mineral admixtures is used. Once again, I would like to reiterate that at the end of it, it's a fixed volume of material, and within that fixed volume, it is our responsibility as concrete engineers to proportion the different constituents, whether it is only the basic constituents as shown here or any other special constituents that we may choose to add in the concrete mix. As far as stages in concrete construction is concerned, we have already gone through it: materials and proportioning, mixing, transportation, placing, vibration, curing. Coming to special concretes, there is fiber reinforced concrete, mass concrete, self-compacting concrete, underwater concrete, roller compacted concrete and shotcrete. These are some of the examples that we will try to cover in this set of discussions here. Now let us look at fiber reinforced concrete, for example. I am not sure whether the picture is very clear, but what is shown is the fibers that are sticking out here between the two fractured faces of concrete, and that is what makes this concrete special. Normal concrete would just fracture, but fiber concrete, because of the presence of these small fibers here, does not fracture in a brittle manner. It still carries some load after the concrete has largely failed. Now, these are the ideas that are important. Where concrete has largely failed means there is perhaps a large amount of deformation which has occurred, but the concrete can still sustain at least some load. Now, let us look at mass concrete. Mass concrete, these are examples of dams or hydraulic structures. These concrete structures are very large in scale, in geometry, and so on. And placing concrete in these structures has certain special problems. One, it is not very heavily reinforced. Number two, we may choose to use large aggregates. Number three, we may choose to use large volumes of concrete in a single pour. Now, the moment we decide to use large volumes of concrete in a single pour, we have the problem of heat of hydration and related thermal stresses. So, once we start talking about a concrete where special efforts need to be made to handle the heat of hydration of cement, that concrete is basically called mass concrete. And that is what we will try to study in one of the discussions that we will have. Coming to self-compacting concrete, we have shown this picture earlier where this concrete is almost like a fluid, it flows, and we use slump flow and the U-tube or the U-box test to measure its properties. Underwater concrete, we have also seen this picture, and you can imagine that it requires a very different kind of concrete which will be required for this kind of placing. The concrete has to be highly segregation resistant. That is, the cement particles should not just get washed away and should not move away. Roller compacted concrete. Now, when concrete is placed in a very open space, for example in a highway, or for that matter sometimes in a dam, then concrete need not be very fluid, because there is enough space for the concrete to be placed and compacted. Reinforcement is very small, and we may use what is called the roller compacted concrete. And this roller here could be a vibratory roller which acts as a form vibrator to this concrete, which has been placed on the surface. So, a form vibrator is applied on the form work, whereas in the case of roller compacted concrete, the vibrator, if it is a roller, vibratory roller, the vibration is applied to the surface of the concrete directly. So, these small differences in technology cause the properties of concrete that are required to be different, and therefore, the concrete engineer is called upon to proportion the mix differently and do quality control in a different manner. As far as shotcrete is concerned, we have already seen these pictures, and we know that concrete which needs to be placed in this application has to be designed very differently from the concrete which is required for underwater placement or roller compacted concrete, and so on. Let us talk a little bit about the mechanisms of deterioration in concrete structures. We know from our experience in the last about 40-50 years that concrete is not a maintenance-free material, and when concrete structures are exposed to different environments, the concrete deteriorates, the reinforcement corrodes, sometimes there is a problem with the material that we use, and that shows up only after a reasonably long time, causing the structures to deteriorate, and so on. And some of the mechanisms that we will take up for discussion here are reinforcement corrosion, alkali aggregate reaction, and cyclic freezing and thawing. So, let us take a look at what reinforcement corrosion does to the concrete structure. If we look at these pictures here, we find that corrosion has caused a lot of damage to this concrete structure. It has caused a lot of damage in this part of the structure here. We can see that the cover concrete has spalled off, has been removed, and the reinforcing bars which are here have been exposed and are very much corroded. The reinforcing bars here are exposed and are corroded. It is the corrosion of these bars that has caused the cover concrete to be removed from the concrete structure. From this, it's equally clear here that at the bottom of these reinforcing bars has caused the concrete to be removed from the structure. Now let's look at alkali aggregate reaction. We said in the beginning of the discussion today that aggregates are all inert fillers. That is true in the normal sense of the word, where normal aggregates and normal cements are being used. Some aggregates, however, have been found to be reactive. That is, they react with the hydration products of the cement paste, and that causes the concrete to deteriorate, and what we call that is the alkali aggregate reaction. So what we see in alkali aggregate reaction is shown here, that is a lot of surface cracks appear on the concrete, and they cause distress, they are visually unacceptable, and also cause problems as far as the structural behavior of concrete is concerned. Now coming to freezing and thawing of concrete structures. Cyclic freezing and thawing, that is, the concrete is placed in an environment, or the structure is in an environment where the temperature of the atmosphere becomes less than 0 and more than 0 or higher than 0, causing the water in the concrete to freeze and thaw cyclically. Now we know that if that happens, the water expands and contracts, and this change in volume of the water which is within the concrete in the pore system causes the kind of deterioration which is shown in these pictures. We can see that the surface of concrete has become very, very poor. Some concrete has been abraded. We can see here that scaling has occurred, that is, on the surface this mortar has been lost. Similarly, in this case here we see aggregate pop outs. Coming to the reinforcement in concrete structures, we know that typically we use steel as a reinforcing material. We will not talk much about steel in this course, but we will talk a little bit about epoxy coated bars and fiber reinforced plastics. These two are alternative reinforcing material to steel and are important for a concrete engineer to know, because they are the answers in cases where concrete is likely to be subjected to reinforcement corrosion. The steel is susceptible to corrosion, epoxy coated bars are less susceptible to corrosion, fiber reinforced plastics are not corrosive in nature, or fiber reinforced plastics are not corrosive, and therefore an engineer should know about epoxy coated bars and fiber reinforced plastics. And let's take a look at epoxy coated bars. Epoxy coated bars are nothing but normal reinforcing bars like this, which have a deposited coating of epoxy material, and this coated material prevents the surface of the reinforcing bar here from corroding. That is, this prevents this surface from being exposed to oxygen or water, which are the necessary ingredients for causing the corrosion. So that's how epoxy coated bars work, and here we see pictures of how epoxy coated bars are placed. They are placed just like a normal reinforcing bar, except that certain precautions have to be taken. This picture here shows bent epoxy coated bars, because when we bend an epoxy coated bar, we subject the outside face of the epoxy coated bar to tensile forces, and the coating here is likely to crack, and that causes, or that requires, that the epoxy coated bars should be properly tested before they are used in a concrete construction. Now coming to fiber reinforced plastics. Now fiber reinforced plastics, or FRP bars, are basically consist of these fibers which are embedded in a resin matrix. These fibers could be made of carbon or aramid or glass, and there are different materials that can be used for resin. And once this structure is set, then it can be commercially available, and these fiber reinforced plastic bars are available in different shapes and sizes, as can be seen in this picture here or this picture here. This one here is a typical example where the FRP bar really resembles a normal steel bar with all the ribs and so on, to ensure that the bond between the concrete and the reinforcing bar is also not compromised. Coming to the last topic that we will try to cover in this set of lectures is the maintenance of concrete structures. Maintenance involves non-destructive testing, evaluation based on non-destructive testing data, and a comprehensive plan for maintenance. Different methods are available for non-destructive testing of concrete structures, and you may be familiar with test methods like the Schmidt hammer or the ultrasonic pulse velocity and so on. We must remember that these methods give us certain numbers, and those numbers actually need to be evaluated. Whether that number is acceptable, unacceptable, what is the variation that is observed in those numbers, and so on. So we will look at some of those issues, and we will talk of the thought process involved in a comprehensive plan for maintenance. With this, I come to an end of the discussion today, and I would like to acknowledge the help and all the support from the Japan Society of Civil Engineers in Tokyo, the Kajima Corporation in Tokyo, friends and colleagues of IIT Kanpur and the construction industry in India, and especially Professor Omoto of the Public Works Research Institute in Tsukuba, who was the Tsukuba in Japan, and formerly Professor of Civil Engineering at the University of Tokyo, who gave me some insight into this wonderful material, concrete, and I hope to share some of my experience with you beginning the next class. Thank you.